Download this code from codegive.com, link in the description below. Locking with async/await, rock-solid knowledge and code examples. Async/await, while incredibly powerful for writing concurrent code, introduces complexities when dealing with shared resources. Ignoring proper locking mechanisms can lead to race conditions, data corruption, and unpredictable behavior. This tutorial dives deep into the strategies for achieving robust locking in asynchronous Python code using asyncio and its associated tools. Understanding the problem, race conditions in async code. Consider a simple scenario, updating a shared counter in an asynchronous context. Multiple coroutines might try to increment the counter simultaneously. Without proper synchronization, this leads to a race condition. The final count might be less than expected because increments might be overwritten. The counter plus equals 1 operation isn't atomic. It involves multiple steps: reading the current value, adding 1, writing the new value. If two coroutines execute these steps concurrently, one's increment might be lost. Solution 1, asyncio.lock. The simplest and often most effective solution is asyncio.lock. A lock acts as a mutex, mutual exclusion, ensuring only one coroutine can access a critical section, the code that needs protection, at a time. Async with lock is a context manager. It automatically acquires the lock before entering the with block and releases it when exiting, even if exceptions occur. This ensures that locks are always released, preventing deadlocks. Solution 2, asyncio.condition, for more complex synchronization. Asyncio.condition provides more fine-grained control than a simple lock. It allows coroutines to wait for a specific condition to become true before accessing a shared resource. Imagine a scenario where a producer coroutine adds items to a queue, and a consumer coroutine removes them. The consumer should wait if the queue is empty. Condition.wait puts the consumer to sleep until another coroutine calls condition.notify, or condition.notify_all, to wake up all waiting coroutines. The async with ensures that the condition is released properly. Solution 3, asyncio.semaphore, limiting concurrent access. If you need to limit the number of concurrent accesses to a resource, instead of just allowing one at a time, use asyncio.semaphore. Let's say you have a database connection pool and want to limit the number of simultaneous connections. The semaphore starts with 5 permits. Each async with semaphore acquires a permit. If all permits are taken, subsequent calls will wait until a permit becomes available. Advanced techniques and considerations deadlocks be very careful when using multiple locks. Acquiring locks in a different order in different coroutines can lead to deadlocks, situations where no coroutine can proceed. Lock-free data structures for specific use cases, consider using lock-free data structures. Example: asyncio.queue itself is often lock-free internally. These minimize the need for explicit locking. Thread safety. If you're interacting with libraries or data structures that aren't inherently thread safe, you'll need to protect them with locks, even in an async context. E.g., many parts of the multiprocessing library are not safe for simultaneous access from multiple coroutines. Testing. Thoroughly test your concurrent code to ensure it handles race conditions correctly. Use tools that can help detect concurrency bugs. This comprehensive tutorial provides a solid foundation for handling locking in asynchronous Python code. Remember that choosing the right locking mechanism depends heavily on the specifics of your application. Always prioritize clarity, simplicity, and testability when designing your concurrent systems. Choosing the wrong locking method can increase complexity and may even introduce more subtle bugs than the race conditions you're trying to solve.